there, welcome to my channel, and if you're new here, please do not forget to subscribe. I hope you've been doing well and keeping safe. So today we're gonna look at another coding interview problem, and I hope you get to learn something from this. So let's do this. So today's question is validate binary search tree. This is a very common coding interview problem, specifically with the company Facebook or Amazon, and that is why you should be ready to know how to solve this problem and also know how to manipulate binary search trees. So the question here is that, given the root of a binary tree, determine if it is a valid BST. And you're told that a valid BST is defined as follows. The left subtree of a node contains only nodes with keys less than the node's key, and the right subtree of a node contains only nodes with keys greater than the node's key. Both the left and the right subtrees must also be binary search trees. So these are the rules that we should follow when it comes to determining whether a tree is a valid BST or not. So we're given examples here. So we have 2, and then towards the left we have 1, and then towards the right we have 3. So 1 is less than 2, which makes this rule number 1 here tick, and then 3 is greater than 2, which makes this tick as well, and that is why we have the output true. So this tree here follows all the rules of the binary search tree, and that is why the output is true. But if we look at the second example, we have 5. 1 is less than 5, that is okay, it follows the rules. But when you look at 4, 4 is also less than 5, and therefore it should not be on the right, rather it should be on the left. Okay, so because of that, our output is going to be false, because this is not a valid binary search tree. So following the rules, we're going to be able to come up with an algorithm that will help us determine whether a tree is a valid BST or not, and that is what we're going to be looking at next. So let's say we have this tree here, and we're supposed to determine whether it is a valid BST or not. Most people would definitely come up with a solution whereby you check whether the items on the left are less than the root value and the items on the right are greater than the root value. So while that seems like an optimal solution, it is actually not optimal because of one thing. It is not going to account for a very important detail, and that is what I'm going to show you. So in this case, we are going to check whether 2 is less than 6, and that is correct. 7 is also greater than 6, so that is correct. So in this case, the solution would pass. But when we come here, we see that 4 is less than 7 and 8 is greater than 7. So the solution here is also going to pass, and it's going to come off that this tree is indeed a valid BST. Well, that is not the truth. The truth here is that the solution that I just talked about is going to overlook the fact that 4 is actually less than 6, and 4 is not supposed to be here. So that is why the solution that I just said would not be optimal, and basically we have to come up with the solution that we have to set a couple of conditions down the tree that we'll have to do the checks and ensure that all the items on the left subtree are less than the root value and all the items on the right subtree are greater than. And so our algorithm should have to include those conditions, and that is what we are going to have on our code. So onto the solution, we're going to make use of a helper function. So in this case, I'm gonna have return self dot, I'm gonna name the function helper, and I'm going to have root, and I'm also going to have 2 values. I'm gonna have a maximum and a minimum value, but in this case I'm gonna make use of the negative and positive infinities. So I'll have float, and we have minus infinity for negative infinity, and then I'm also gonna have the positive infinity, so which is going to be this, and that is how to represent negative and positive infinities. That is another way of representing the positive and negative infinities in Python. So I'm gonna go ahead and make the helper function. So we have define helper, and then we have the self, and then we have root, and then we have a minimum value, and then we have a maximum value. So the first thing that we want to do is that we want to check the root. So I'm gonna do if root is none. What we are gonna do is that we are going to return a true. So I'm going to return true, because that means that our tree is a valid BST. And then afterwards I'm going to do another check. So I'm going to do if the current value is less than or equals to the minimum value, or if the current value is greater than or equals to the maximum value. What we want to do is that we are going to return a false, because that means that it is not a valid BST. Otherwise, what we're going to do is that we're going to keep traversing the binary search tree and return true or false depending on whether the left and right subtrees are actually valid binary search trees as well. So I'm going to have a variable here that is going to keep track of the left subtree, so valid left, and what you're going to do is that we're going to traverse, so self.helper, and then we have root.left, and then we have the mean value, and then we have the root.val. So I have a problem here, it's supposed to be mean val. And then we also have another variable which is going to keep track of the right subtree, so I'm going to name it valid right is equals to self.helper, and then I'm going to traverse the right subtree, so it's going to be root.right, and then we have root.val, and then we have the maximum value. So after doing that, we want to go ahead and return true if the left and the right subtrees are actually valid BSTs. So I'm going to write this function which is going to take care of that. So it's going to return valid left and valid right. So this function here is going to return true if our left and right subtrees are actually both valid BSTs. So to reiterate what the program here is doing, our program is ensuring that all the items on the left side and all the items on the left subtree are actually less than the root value, and all the items on the right and the right subtree are greater than. And that is achieved by the recursive calls here. So this recursive call is going to ensure that all the items on the left subtree are indeed valid, and all the items on the right subtree are valid as well. And by valid I mean that they have to be less than if they're on the left, and they have to be greater than if they're on the right. And the reason why we have the negative and positive infinity is because we need to keep track of the minimum value and the maximum value that any left subtree or right subtree can have respectively. And then that is how to write the algorithm, or rather the functions, to solve this problem here. So let's go ahead and test our code. And our code has been accepted. I'm going to go ahead and submit it. And yes, so our code seems to work fine, and that is how to approach this problem in case you're asked in an interview setting, or in case you want to learn about binary search trees. So I hope you've learned something, and I will see you on the next coding problem. So thank you and keep safe.